Now, to be honest, Coulomb's law would have been taught to all of you last year in AP Physics 1, but due to our unfortunate circumstance, nobody got it. Your teacher might have just started, but the truth is, most people, like I skip it. I do electronics first, and then I come back to it because it's just really boring. We don't do very much with it in AP Physics 1. We're going to do a lot with it in this class, and because of that, I need to be very critical about how we learn it. But at the same time, I'm going to assume that nobody has actually used this at all, and we'll start from scratch. Coulomb's law is very similar to Newton's law of universal gravitation. So for you guys who have been in a physics class before, you know that the law for gravitation, Newton's law of universal, I don't know why I'm writing it all out. How many of you are finding now that you're writing notes that you have forgotten how to write things? Like it's been like 4 months since you've written stuff and your handwriting is terrible and you're just realizing how terribly bad it is. And every time you go to write, you keep using your thumbs because you usually type these things out. I bet that's a lot of you. I mean, maybe not as many of you as I'd like to think it is, but if I was to have two objects, call it M1 and M2, separated by a distance r, I could state that the force of attraction between them. First, it would be the same on both objects. They feel the same force of attraction, and that force is equal to the product of their masses divided by their separation distance squared times a constant that will convert these units into a force. This should be a review for everybody who had physics class last year. This was called the gravitational constant. It's a universal constant that we believe is the same everywhere in the universe. And it's a scaling value that's based on kilograms, meters, and seconds. And just for poops and giggles, 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. So a very small number because the force of gravity is relatively small. It takes a lot of kilograms to get a little bit of force. Coulomb's law is almost exactly the same. If I replace this with a symbol representing charge, the traditional symbol for charge is either a capital Q or a lowercase q. That is the traditional symbol for charge. I know, a C would be nice. But, it's physics, so to represent charge, we use Q, because that makes sense. Coulomb's law is Q times Q divided by R squared. Of course, there also has to be a constant here. Something that's going to put the thing in the correct units. This is often called the Coulomb's constant. They use a lowercase k because his name starts with a C. I don't know. I didn't make these things up. We will only use the Coulomb's constant for a short time, but the Coulomb's constant is, if you use your book, it's 8.99, but we're just going to use 9 times 10 to the 9th newtons meter squared per Coulomb squared. That's right, Coulomb squared. Why? Because the unit of charge is the Coulomb. And as I was trying to say yesterday, it is an intrinsic property of matter. There is no definition to Coulomb. Just like there's no definition of kilogram. I have examples of kilograms sitting in some lab someplace, but there is no definition. It's an amount of mass. So Coulomb is an amount of charge. Now, again, 1 electron's worth of charge is 1.6 times 10 to the negative 19th coulombs. And I'd be remiss if I didn't make at least a little bit of a deal about this. That's a very small number. The actual idea of Coulomb is big. So a single Coulomb of charge is potentially problematic. It can cause, second degree burns should you be discharged with a Coulomb's amount of charge. Nature abhors separation of charge. So building up a Coulomb's worth of charge is really hard to do. If you ever have to have a defibrillator applied to your heart, they're going to pass about a Coulomb's worth of charge through your heart to try and get it restarted or get it on a regular rhythm. And to prevent it from burning you, they will put a kind of a lotion on the pads, an electrostatic lotion to transfer the charge through your skin without the charge itself having to penetrate the skin dry and burning you. So when we talk about a Coulomb, it's a lot of charge. The electron is a ridiculously small amount of charge. But, and this is the most important thing I'm going to say today, that charge is quantized. Most of you don't know what this word means, so I need to explain it, but get it down in your notes. It's quantized. What that means is that there is a finite minimum amount of charge that can exist in the universe. The way I like to explain it is think about pennies. I can't ask for a half a penny's worth of money. There is no such thing. So if I say I just want half a cent, I can't give that amount to you. I can either give you a whole cent or no cents. So there's never a value of charge less than this. If you work out how much charge needs to be there and the number is less than that, your answer is wrong. But it also means that all amounts of charge are some multiple of this. So if I have 6 electrons, how much charge do I have? I have 6e, or 6 times 1.6 times 10 to the negative 19th coulombs. How much is that? That's the charge on a carbon atom. It has 6 protons, 6 electrons. The proton has the exact same amount of charge as the electron. The difference, and the reason why we don't base the Coulomb on the proton, is twofold. First, the proton is inside a nucleus, hard to isolate. But second, a proton is made of multiple particles called quarks. And because of that, the electron is not. It's a lepton. Leptons are single particles that exist on their own and can't be broken down into smaller pieces. Protons are hadrons. And because of that, they're broken down into quarks. The quark model is actually something that is completely subject to the charge being quantized. The quark model predicts that there can't be a part of a proton. In fact, a proton specifically is 2 up quarks and a down quark. At least in normal matter it is. In other forms of matter, it's 2 top quarks and a bottom quark, or 2 strange quarks and a charm quark. But in our version of matter, it's 2 up quarks and a down quark. Up quarks are positive 1/3 elementary charge. Down quarks are negative 2/3 elementary charges. No, I'm sorry, I reversed that. I was wrong. Up quarks are positive 2/3, and down quarks are negative 1/3. Quarks will only assemble in combinations that produce a whole number amount of charge. None of this is actually on the test, but I think it's interesting. So what that means is all normal matter has to form in such a way that you either get a full amount of charge, 1e, or zero charge. So most of you here should be able to figure out what the combination of quarks is to make a neutron. You got it yet? Shouldn't be hard. Should be 1 up quark and 2 down quarks is a neutron. This is the quark model. Now, the quark model has been incredibly successful at predicting nuclear events. And currently, this particular structure of matter seems to be very well represented in the literature. There are exotic forms of matter that apparently seem to pair together only 2 quarks. But they tend to exist using quarks of different types. The up and down quark is one type of quark, the top bottom quark is a separate type of quark, and the strange charm is a third type of quark. So there are forms of matter that are more exotic than what we see in our everyday existence. But the big thing I need you to remember is the quantization of charge and how much charge there is in the electron and the proton. Now, generally, these questions aren't huge. This is not going to be a huge part of the test, but please understand, if I tell you you have 5 microcoulombs of charge, you should be able to tell me how many electrons or how many protons that is. And some students have a difficult time with that idea. Remember, this is a conversion fact. It converts number of particles to coulombs. Coulomb's law. That's where I kind of want to focus now. When we focus on Coulomb's law, there are a couple of things to which we really need to pay attention. First, Coulomb's law is a little more complicated than I described. Coulomb's law is a vector law. And should be written more like this. We're going to need to learn a little bit of symbology that you didn't have before. R hat. There's an actual name for that, and it's not a tilde, but I don't remember what the little caret above the R is. But I'm going to call it R hat. R hat is a special kind of symbology we're going to use in this class quite a bit. It's a vector notation, but it's a special kind of vector notation that indicates for us a unit vector. A lot of students have trouble with the concept of a unit vector. A unit vector denotes direction and only direction. It points somewhere. It is 1 unit long, so it doesn't affect the numerical magnitude of an answer, but it implies direction. Force, by definition, is a vector quantity. It has to have direction. But in this relationship here, the only variable that could possibly denote direction is squared and in the denominator. Therefore, it can't denote direction. The moment we square it, it strips off any potential to have direction, right? Negative numbers would become positive. So any potential for it to have direction is gone the moment it's squared. And the fact that it's in the denominator, even worse. So our full definition of Coulomb's law must include a way for us to have a point of reference that indicates the direction along which this force would have to apply. More importantly, if you have 2 charges, Q1 and Q2, Coulomb's law predicts 2 forces, not 1. It predicts that there is a line that joins these 2 things together, and that the force acts along this line. That's what the R is trying to get at. That if I want to know the force on particle 1 from particle 2, the force on particle 1 from particle 2, then I would have to draw a line from particle 1 to particle 2. And here's the deal. The force on particle 1 from particle 2 means particle 2 is the origin. It's the point of reference. So the arrow from particle 1 to particle 2 is in this direction. So r hat is a unit vector that is in that direction. It goes from particle 2 to particle 1. So, in order for Coulomb's law to be consistent, there is an explicit negative sign in the front of Coulomb's law to indicate the direction of the force on particle 1 from particle 2. The force in this case would be back along that line, assuming a force of attraction. Just so you guys know, all of this is to correct for the fact that the electron was made negative. Because listen, this is important. If Q1 and Q2 are both positive, my answer here is negative, which means the force is towards the origin. If either one of these particles is negative, it cancels out the negative sign out front, making that force positive, which means that the force is away from the origin. If both of those particles are negative, then my answer is again negative, which means my force is towards the origin. This is the mathematical way of saying opposites attract and like charges repel. Now, let me just, for just a moment, bring us all back to center for a minute. I am making this terribly complicated to prove a point. If you can keep in your head that like charges attract, that unlike charges attract and like charges repel, you would never have to worry about any of this stuff. This is here because our mathematical symbology has to be consistent, and we need an agreed upon consistency in our math to represent both vectors and magnitude. This is how you do it. It's not pleasant, and it's not easy. But it's important that we understand that we're not always going to be dealing with 2-point charges in space. That problem is easy. I want you to imagine what's going to happen in about a week when we'll go route of giving you this complication for what this has to look like, so that you would have an appreciation for where we have to go with this math. Because where we actually have to look at looks a little different than that. Maybe something, here, let me think of a quick example because I'm going to run out of time. Like this. So imagine I have a bar of charge. The whole thing, uniformly charged bar. So it's all, I'll make it easy. Let's say the whole thing is positive. And I have a charge out here that is also positive. That would mean that this portion of the bar is going to push the charge with a force in this direction, right? It will repel. But this portion of the bar is going to push the charge in this direction. It's further away, and it's going to push in a different direction. If I asked what the total force on the charge is, do you realize I'm going to have to take into consideration all of these different unit vectors and how much each one contributes to the amount of force acting on that particle? So I'm not trying to convey this as being terribly, oversimplified. I'm saying we need to have a way of expressing this mathematically so that when I get a complicated scenario, I can carefully consider how the direction will influence the answer. By the way, this problem, probably outside your abilities to do. But on the other hand, if I put that charge, say, in the middle of the bar, that's not really the middle. Let's try more middle-ish. There, that's the middle. In the middle of the bar, this problem is inside your abilities to do. It's not easy, but we will do this problem, or at least set it up. So I want this to go with this math is to take something like that works on point charges, and take an object like this and break it up into a bunch of individual points, and then add up each one of those points' contributions. And some of you know where this is going directly because you've had calculus already. Some of you have not had calculus yet and don't understand that this symbol means to add up. We will have to add up all these small contributions to the force. So